Okay, so yeah, there is nothing special about the backpropagation in the RNN or LSTMs. So in this particular example, it's a many-to-one model where we had a in this example we had a 3 different time steps as an input sequence, and then output was Y3, and then yeah, it can be viewed as a many-to-one kind of model where we apply our ground truth label on this third time steps, right? And then the gradient will be flow this way and this way and this way, right? So reversing or this backpropping over the time steps towards the earlier time steps is called a backprop through time, right? And then here in this example, we consider this gradient kind of explosion and vanishing problems, but at the same time, yeah, so if you remember, we considered the gradient corresponding to H1, right? But now in this case, what about the gradient corresponding to H2? In this case, the gradient will be just this guy, A and 1/2 and D, right? And then we have a gradient corresponding to H2, and then also gradient corresponding to H1, and then those two different hidden state nodes at a different time steps. Okay, so so we understand the patterns of how they are computed. Basically based on geometric sequence, right? But in terms of our parameters, what is our parameter in this case? Of course, A, B, and C, like these values. A, B, C, and maybe D and E, right? So in this case, let's just focus on this. A, B, and C. And then, also let's focus on this A. So in this case, because it's a recurrent neural network, they share all these parameters across different time steps, right? And then in that case, we can view it as this kind of form. So let me redraw. So these are x1, x2, and x3, and then we have a y3 here. But here, so this one is h1, right? And then in this case, I'm trying to redraw this figure more explicitly as a computational graph. So here we had, suppose we have a node here. So we have a node for the parameter A, right? And in that case, so this one H1 is multiplied together and then added together. So we have AH1 and BX2 and so on, right? And so here in this case we have like B here, and then more exactly, so let me just erase this, and then they are multiplied together and then added together, right? And then we have C here, and then they are also added, right? And then this one is corresponding to this node, right? And then what about computing this H3? So in this case, it's a little bit ugly, but we are just drawing the same computation graph. But here in this case, we are reusing our parameters, like this guy, right? And then maybe multiplying it and then add it together, and then this C is also added together, and that will form A3, right? So in this case, let's focus on this A, B, and C. So these same nodes are connected through different time steps, right? And so it's like, So we have an A node here, and then they are branching out into multiple kind of nodes in this downstream or this forward pass. And then what about the gradient? So the gradient is occurring in each of these nodes, and then they will be all added together to form the total gradient of an A, right? So in this case, yeah, so A is connected over here and over here, right? And then this one is H2 and H3 and maybe H1, and then we know how this gradient for H3 to 1 are formed at this point, right? And then they are backpropagated through this pass and through this pass, and eventually these multiple passes, gradients from this multiple pass are added together to form the single gradient A, right? But still, the nature for the gradient of this A is basically geometric sequence, because the gradient corresponding to H1, 2, 3 is a geometric sequence. I mean, H3 is our first item in the sequence, and 2 and 1 and so on. So these will be geometric sequence, and then, yeah, from our backpropagation, yeah, the gradient will be shown as a total sum of all these gradients from these passes, from this pass, to compute the gradient of an A. And B and C are exactly the same. So this is yeah, how we compute these gradient, right? And then so this is my own kind of, yeah, slide, and most of which were made by my other students. But yeah, you can download this file by just typing this tiny URL, and then it's a KUNLP and RNN. I mean, yeah, I'm just trying to give you this URL so that you can just download immediately. Then yeah, you will have this file. It's nothing. Yeah, there's nothing special about this lecture, but let's see. Yeah, so in the case of a many-to-one model, so we have a long kind of sequence of words. So I studied very hard, and then I slept, and then yeah, and then at the end we can do like many-to-one model of maybe sentiment analysis, or if we do the language modeling, and then we are performing the prediction task on every time step, and then we have a ground truth over here, and then they will be added together as well, right? So it's like our A and B and C are over here, and then they are all connected to each other, right? And then the losses are like occurring from multiple outputs, and then they are backpropagated, and then yeah, some are added here, and then they will be also added towards the same common parameter A and B and C. But because of this geometric sequence kind of nature, so it will either explode or vanish, I mean the gradient. And so we typically use this truncated backpropagation through time. Or yeah, so backpropagation through time is, yeah, it doesn't mean any kind of a special kind of stuff, right? But yeah, people often, yeah, use this term, and then also this acronym for this is a BP kind of TT, right? Okay, and then in order to avoid this geometric sequence being exploding, so we are truncating our entire sequence, right? So if our sequence is too long, and then we just chop them off into multiple pieces, and then yeah, we use it as a one single data instance or one single sequence, right? So in this case, in the case of a character level RNN model, let's see. So if we train this character level RNN, and originally in this case, yeah, it's like, yeah, you guys know what the character RNN is, right? So if we have a word of one hello, HELL, and then we are trying to predict the next immediate character, right? So this is a character level RNN, or character level language model. Okay, then in this case, we try to train our RNN model by using this single very long sequence, right? So we have only one sequence, but this sequence, when given L was an input, and then the predicted character should be E, which is this next character, and T, and so on, right? So in this case, we essentially have one single sequence, right? Although it's a many-to-many model. So what we typically do here in this case is to chop them off with certain lengths, and then form this multiple data instances or multiple sequences. Okay. So here in this case, one drawback or one limitation is that. Okay, so marriage, and then this, in order to maybe predict this word E, it cannot utilize any information about the word shown in this previous sequence, right? But still, I mean, this kind of very long dependencies doesn't exist much, so that's our assumption to be able to do this chopped version of our data instances, and thus the backpropagation also is performed in that manner. So as if we started our sequence just from here. Okay. So that is also called the truncated backpropagation through time. Okay. And then I think you guys all understand how LSTM and GRU works, right? 이거 다 알죠? 기본적으로? 네? 한 20-30번은 나도 개인적으로 설명한 것 같은데. 하여튼 이거 하여튼 안 다치고. Okay, so in this LSTM or GRU, why can we avoid a gradient vanishing or explosion problem in this case? So I wanted to discuss about it. Let's see. So in the case of an LSTM, essentially the hidden state information is conveyed in the cell state, right? And then this cell state is further transformed with the 10H, because this cell state can have a range from negative infinity to infinity, right? And then it is further transformed into by using 10H, and then we also apply this output gate so that we can hide those information that are not directly useful for generating the current time steps output in maybe YT or something, right? Okay, so this cell is essential information that we carry out over or across the time step, and then basically this cell state is updated based on this formula, right? And then in this case, so we have, so where did our geometric sequence come from in the previous case? In this case, so H1, H2, and H3. So there are operations that transforms H1 through H2 is based on this linear transformation A, and then also this guy 10H thing, right? 10H thing. So if A is greater than 1, and then that is the main cause of a gradient explosion, right? Because we keep multiplying A over and over, and then this 10H thing, that also be multiplied over and over, right? At each each hidden state node will have a 10H, and thus we will just multiply their slopes, right? As we go through the as we do the backprop across the previous time steps. But in this case, this is the updating formula of our cell, and then in this case we can avoid this gradient vanishing or explosion. And what is the reason? What is the reason? Okay, so let me describe what I think, or my opinion. So from ht minus 1, so we multiply a, right? And then we go through 10h, right? And then this parameter is actually the same one, which works as a common ratio in our geometric sequence, right? But here in this case, let's look at the evolution of ct, or ct minus 1. So ct minus 1 will be multiplied with what? ft, which is a element-wise multiplication, right? And then what? I mean, the addition doesn't matter because the gradients are separated, right? So if we just track back the gradient from ct to ct minus 1 and then ct minus 2, and then these addition will not matter, right? And then this one will be just our ct, right? And in this case, let's look at what is multiplied here. So we are multiplying a here, and then here something called a forget gate, right? And in this case, this can range from, of course, minus infinity, negative to positive infinities, and then this ft is ranging from 0 to 1. But in this case, there is no more common ratio in this case, because this ft is computed differently at every different time step, right? So it can be maybe 0.3, and also in the next time steps it can be 1 or 0.8 and so on. So in this case, we no longer are restricted to this common ratio thing, right? ft is computed as a different value at different time steps, right? And then also, we do not go through any nonlinear units in the evolution of this cell state, right? So it is basically recursive, right? I mean, this ht will also be multiplied with a and then 10h, and then that will generate ht plus 1, and then also this ct, and then will be multiplied with this ft plus 1, and that's it for generating ct plus 1, right? Okay, so this in terms of a gradient, if this guy is 1, and also if this guy is 1, and then the gradient coming from this guy will be just remaining as the same gradient when they are backpropagated to ct, and then when backpropagated to the ct minus 1, if ft is 1, and then the gradient will be just remaining as the same one, right? Remaining as the same one. And then it sounds like a little bit difficult condition, because across multiple different time steps, ft should remain as 1s, right? I mean, at every different time steps. I mean, that's how we can preserve the original magnitude of this gradient, right? But it's actually not difficult, because this ft is what? Ft is basically an output from this sigmoid gate, right? Sigmoid gate, and then in terms of our sigmoid function, so here 0.5, and then what is the region? What is the region that will generate the sigmoid output as 1? It's actually quite large. So maybe around here, suppose it as 2, and then if the linear transformation output is greater than 2, and then their sigmoid output will be close to 1, right? So it actually has really wide range of generating this sigmoid gate as 1, right? Across different time steps. So okay, so that way, we don't have any 10H thing. So in the case of 10H thing, the range of when backpropagating it, we have to multiply their slope, which is having the range between 0 and 1/2, and thus if this guy gets multiplied over and over, and then it's like multiplying maximally as this guy, right? But we don't have such a restriction for our cell state, right? Because cell state doesn't have any nonlinear units, so we don't need to keep multiplying gradient or the slope less than maybe 1/2. Okay, so that way, it's a much easier situation that we can preserve the gradient from really far end, I mean from the far time step towards the really old time steps. So that's how we can do this, that's how we can take care of this long-term dependencies quite easily, right? Okay, so that was about the backprop of RNN or maybe LSTMs. Okay, so any questions about the lectures? Okay, then let's discuss about this beam search. Okay, so can anyone explain how this beam search works? I mean, it's okay even if you just describe it in Korean. Can anyone explain how it works? Okay, I don't understand what this silence means. I mean, whether it's a sign of a sign that you understood, all of you understood, or none of them understood, or maybe half of them understood, or something like that. But anyway, so let's go through this beam search step by step. So one thing that actually I was confused about is this beam size is not about the kind of step of look ahead kind of thing. So it's not about the looking ahead, like 2 time steps further. Yeah, it's not like that. Okay, so we still do this kind of greedy approach that just considers just next immediate time step. Okay, so that is the there is one caveat about this beam search. And so here in this case, starting from this start in our in the decoding phase, maybe I go to school, and then 나는 교회 간다. 네. So suppose we are doing this decoding phase, okay, and then from here, yeah, we will compute the softmax probability across all the Korean words, right? And then if we are using the beam size as 2, and then we will pick up, or we just consider just 2 like top probability ones, okay? So 2 highest likely words. Okay. And then from here, we consider 2 different scenarios where the first one was 나는 and the second one, yeah, so this one is 나는, and suppose the second one was 내가, for example, okay, and then in the case of 나는, and then we will put it into this next time steps input word, and then try to generate the the most probable keywords in as the second time steps output, right? And here, yeah, I don't think this figure is correct one. It's a little bit misleading, or even I think it's an incorrect one. Okay, so from here, we consider all the possible keywords. Okay, by using or by considering all the softmax probabilities across entire vocabulary in the Korean kind of dictionary. Suppose we have a Korean dictionary as dictionary size as 5, or maybe just 5. Okay, so let's suppose we have a 5 different keywords existing in our Korean vocabulary, and then we will have the 5 different probabilities. And suppose this probability was 0.3, and this one was maybe 0.25. So this is top ranked one, and then the second ranked one among the 5 different keywords in the first time step. And then in the second time step, we compute all the possible probabilities by just directly taking into account our softmax probability. And then suppose this one was 0.1, and then maybe 4, 0.2, and 0.2, and 0.1. Okay, and then this guy, in this scenario where the first keyword is 내가, and then this one will generate its own 5-dimensional softmax probability, right? And then at this point, so we are considering like 2, which is our beam size, and then times the entire vocabulary size, because at each scenario we are considering all the possible keywords in our vocabulary, and then compute the joint probability, right? And then we consider their product, right? And then also 0.25, and then compute all these probabilities. And then, yeah, so we consider basically 2 times the possible cases and their probabilities. And from there, we select the top 2 highest probability one. Okay. And then it could be selected from, yeah, maybe it's a 2, 5 and 1, 5, and it could be selected from one branch as maybe this guy, and then this guy. Okay. Or it can be also selected as maybe one as the top branch, and then the other one as this bottom branch, because the bottom branch, suppose we had really a big probability of 0.6. Okay, so in this case, yeah, we can have the second ranked one found in the second or this different branches. Okay, so in this case, we basically keep those 2 branches. Okay, but anyways, we have two different possibilities as of the length 2, and then from here, so we do also the softmax, okay, on these two different scenarios, and then we compute these probabilities of these 3 keyword sequences, and then choose the best or the maximum, the 2 maximum probability ones. Okay, and then sometimes it can be merged into, I mean, the 2 can be found in the same branch or still in the different branch. Okay, and then we do this over and over until we generate the maybe end of sentence token and things like that. Okay, and then as we grow this tree all the way to the end until we meet this end of sentence token, and then we still consider just two possible kind of branches, and then we finally pick up the largest probability one between the two, and that will be our final answer of this beam search. Okay, so here the point is, in terms of this computational complexity, let's see. So when considering all these possible cases, if our vocabulary size was 5, and then if we consider all the possible cases, and then 5 times t, where t is the sequence length, right? But in our case of a beam search, what will be the computational complexity, or the number of cases that we consider at each time step? Okay, at each time step. So we will have just 2 scenarios where our beam search size b, or maybe some other letter, and then our vocabulary size v. Okay, so this is the cases that we consider at each time step. And then how many time steps? We consider maybe t time steps, and then this one is our total number of considerations that we have to compute. Any questions about this beam search? Okay, so honestly, I think I studied this beam search maybe about like six or so months ago, and then I probably studied this beam search a few more times earlier than that. But I also I actually forgot how it works until maybe yesterday, and then this lecture didn't help much in making me understand this beam search. So I searched for some other useful kind of a resource, and then I found this resource of deep learning AI lecture given by Andrew Ng. So I think this lecture is quite, I think this lecture is quite useful. Okay, so I strongly encourage you to watch this video, and also it has some other pieces of like refining beam search, and I actually I didn't know about this until watching this video, maybe until yesterday. And, let me just describe this. And so here, in this beam search, there is one kind of a pitfall or kind of a limitation. So in this case, we are considering the joint probability. So if we are considering the sequence of maybe 나는 학교에 간다. And then what is the probability of generating this sequence? We just consider the probability of generating 나는 as 0.3, and then 학교에 as 0.4, and then 간다 as maybe 0.2, and then we just simply multiply them together because we consider the joint probability of observing that exact sequence, right? So in that case, yeah, in practice, we have one more token in our vocabulary, which is the end of sentence token, right? And then that will also have its own probability value. And suppose like 나는, and then that probability was really small, as maybe 0.03 in this case, and then the output sequence will be just 나는, and then that will not be a correct one, right? So in terms of a language model, it is a quite poor result, and also it is reflected by this really small probability of seeing this end of sentence token right after the token as 나는, right? But still, in this case, because the sequence just ended by using these two tokens as 나는 and end of sentence token, and then the joint probability will be 0.3 times 0.03, right? And then that will be the joint probability of observing that particular sequence, right? But if we, suppose we took this kind of thing, and then maybe the sequence length was about maybe 10 words, right? And in that case, observing each particular words across this 10 different time steps or 10 different keyword sequences, the probability will be smaller than 1, of course, and thus such a number or such a probability will be multiplied 10 times, right? And thus, even though it was really big, up to this point, but as we consider the next particular keyword and then the next one and the next particular one and so on, the probability will become smaller and smaller and so on, right? And thus, in that sense, if we compute this total probability, and then our beam search will prefer shorter sequence of sentence as a higher probability, right? So you guys understand, right? So I'm not sure if I was clear about explaining it. So in this length normalization technique, so they have this normalization term. So what that means is, so we first consider this log thing. So it's basically for the purpose of avoiding this underflow, because if we keep multiplying really small, tiny probabilities over and over, and then that number will be close to 0, that cannot be properly represented by our computer, and thus we just sum these log version of our probability, and then we just take the average of it in terms of the number of in terms of the length, sequence length. So in that case, we consider the average probability of a particular token, regardless of the sequence length of our generated sentences, right? But in this case, if we just normalize it as just the length of the tokens or the number of tokens, then it will be just computing the average probability. But if we consider this kind of normalizer, where alpha is set as less than 1, like 0.7 or even 0, and then it's like in between of the total sum of the probabilities. I mean, considering the total sum of the probabilities or the average probabilities, okay? Because if alpha is set as 0, then it will be just a 1, so it will have no effect, and thus it will just compute or consider the sum of these log probability, right? And in this case, of course, so So we are adding the logs, right? And thus, yeah, so don't get confused. Like, so if we keep adding log version of the probability, wouldn't this value become bigger and bigger or larger and larger? It is actually not, because the log of the probability, because the probability is less than 1, and thus we keep adding the negative value of this log probability. Okay, so that was this length normalization, and then in this lecture series there is another lecture about this beam search. It was also quite interesting, and I actually learned as well. So in this lecture, the main point is, so our beam search based decoding is not perfect in a sense that it doesn't generate the kind of a sequence that is corresponding to argmax. So the sequence generated by beam search, which is still like checking the next immediate output only, right? So in that case, the resulting sequence, resulting single sequence, may not be the one that has the largest probability across the entire search space. Like, yep. So definitely we didn't search for that entire space, right? So our solution or our generated sequence may be suboptimal, right? So the really true answer that has the largest probability may have a different sequence, right? So if our decoded answer or predicted answer from this decoding phase, if that answer was completely quite different from the ground truth answer, then maybe the fault or the cause of such misprediction or the poor prediction may be due to either this imperfect beam search algorithm, or maybe it's due to our improperly learned RNN model, right? So our RNN may have fault, or this beam search may have fault, right? And so we can kind of judge between these two cases. So this is how. So this is our ground truth sensor, and this is our predicted sequence generated by beam search. Okay, and then from this sequence, we basically have a language model that is represented as our decoder, right? And then suppose we generated this ground truth sequence as an output of our RNN decoder. And then we can basically compute the probability, the joint probability of this particular sequence, right? And then of course, our RNN is basically a conditional language model. Conditional language model, so we have an encoding vector coming from our encoder, given this source sentence, right? And then this is a translated sentence, right? And so, we have our initial encoding vector generated by our encoder model, and then we can evaluate the joint probability of this particular sequence, and this is our suboptimal, but that is kind of the answer generated by our beam search, right? And then we can basically compute their joint probability, and then which one is having a bigger probability, okay? So in this case, if RNN thinks that this one has a higher probability than this one, okay, and then which side of fault is there? In this case, between the imperfect beam search and imperfect RNN language model, if the probability of this guy is smaller than that one, then our RNN still think that this one is a better answer than that one, right? So in that case, it's RNN's fault. Our language model should be more improved. But in the case of, in case this guy has a larger probability from our language model than this guy, which is our suboptimal answer generated by beam search, and then our beam search failed to find much better kind of output that has the higher probability. So in that case, beam search is the bad guy, right? So that is the cause of our misprediction. Okay, so for each of our training cases, we can do this kind of evaluation of which fault does this belong to, and so if decoding beam search is the main cause of our misprediction or lower kind of performances, and then we have not much thing that we can do, right? Because beam search is an imperfect one. So I mean, in order to improve it, we have to just increase our search space, like increasing the beam size a lot more. Instead of using the beam size as 2, we can increase the number of this beam size. Or if RNN is basically a fault, I mean that is not a perfect language model in this case, and then we have to improve our decoder by supplying more data or using more regularization and so on. Okay, so that's when we have to focus on our model. Okay. So that was about this beam search. Any questions? Okay, and then let's discuss the different attention mechanisms. Okay, attention mechanisms. So in this machine translation task, where we have this 4 different words, and then we have to keep decoding each of our words. It can be 4 words or even more. In this case, suppose this guy is our hidden state vector, and then in order to generate this attention vector, so what is the attention? So this encoding vector and then their weighted average vector is called context vector, right? And then how we compute the weighted average on these encoding vector is determined based on this attention weights. So for example, it's 0.1 and 0.2, 0.1 and 0.6. So in this case, these are attention weights, right? Then we do this weighted average of these encoding vectors, and then I'd like to discuss about several different strategies of how we compute these weight values. Okay, and then these weight values are basically generated by the softmax layer at the end. Okay, softmax layer at the end, but just before the softmax layer, it will be computed several different ways. So the simplest one is this guy, is as follows. So we have a hidden state vector here, and then we just compute the inner product with this encoding vector of each source word. Okay, so this is the first one, and that several different variations of our how we compute this attention weight is shown in this paper. Nope, maybe not this one. 그 페이퍼 뭐였죠? 이 페이퍼가 아니었는데. Maybe this one? Isn't it the same one? Yeah, I think it's this one. Okay, yeah. NLP. 뭐야 이게? 그 페이퍼 어디 갔죠? Okay. Yeah. Okay. Okay, so that approach is described by the first method, right? Okay, and then the second approach is just using something called a bilinear transformation or something like that. So in this case, we have a four-dimensional encoding vector and also hidden state vector in our decoder, right? And then we can also define the linear transformation output that will be given to our softmax layer as this guy. And then we have the matrix W here. So let me just match the color. Okay, so in this case it's called like a bilinear model, and then so basically it's 1 by 4, and then it's 4 by 4, right? And then it's 4 by 1, right? And then the resulting value will be just a 1 by 1, right? It's a scalar value. And then suppose this one is x1, 2, 3, 4, and this one is y1, y2, y3, and y4. And in this case, this value is actually computed in this manner. So we basically compute all the cross product between these two vector elements between these two vectors. So if we imagine the inner product, and then this x1 will be multiplied only with y1, and x2 with y2, and so on. So that is the definition, I mean the original definition of this inner product. And then in this bilinear kind of stuff, this is defined as by computing all the possible product between these two, elements between these two vectors, x1, y1, and x1, y2, and x1, y3, and so on. And then we basically compute or determine all the different linear combination weights of all the different cross product between these two vectors. Okay, and then let's see, x1 and y2. So suppose this value 3 is over here, and that value is actually placed in this guy, 1 comma 2, yeah, this value, right? And then yeah, if you imagine like the inner product between this guy and then also this guy, yeah, and then yeah, suppose this is 3, 4, 5, 6, and then it will be 3 times x1, 4 times x2, 5 times x3, 6 times x4, right? And that value, I mean, this part will form this a single 4-dimensional row vector, and in this row vector it will form this second element, and that second element will be multiplied with y2, right? Okay, so x1 times y2 will have the linear combination coefficient as 3, and then x2 and y2 will have the linear combination coefficient of 4, which is corresponding to here, right? And then 5 is about the linear combination weight for the cross product of x3 and y2 over here, okay? So this matrix W is basically collecting all the linear combination weights, okay, in this linear combination of all these possible cross product between these two vectors, okay. So this W is of course trained, I mean, yeah, that is determined based on our backpropagation, right? So this is called a bilinear model. And why is it called a bilinear model? It is basically linear in terms of, or with respect to, this product between these two elements from the two vectors, okay. So that way it's called a bilinear model. And in this bilinear model, we are no longer restricted to the same dimensional vectors between this x and y. So suppose our vector y was this 5-dimensional vector, okay, and then in this case still we can consider all the possible cross product, x1 y1 all the way through x1 y5 and x2 y1 all the way through x2 y5, okay, and then we can still consider this linear combination weights of all the possible cross products, and then we can simply set our matrix W as 4 by 5, okay. So in that case, we can also construct this bilinear model between the different two vectors or with the different lengths. Okay, so that is, let's see, that is this guy. So dot product, we have a dot product. It's a kind of a generalized version of the similarity between these two vectors. And yeah, and then the last one, last one is about basically computing the neural nets. So we have 4 different, and let me just move here, this x vector, and this y vector. Okay, and then we just basically perform some linear combination. I mean, maybe we reduce the dimensionality into maybe 4, and then that's how we constructed the first layer. And then the second layer will be like computing the 4-dimensional vector, because this 4 is basically the basically the same as the input sequence length, right? So that way we first performed, in this case, so we pick up, this guy. This guy is fixed one, and then we bring each one of them, I mean one by one, okay? and then this guy is over here, and this guy is over here, and then we do this linear transformation, and yeah, I was a little bit wrong here, and then we are trying to do the linear transformation with a single value, just a single value. Okay, and then here, because we perform the linear transformation, and then we can do the nonlinear unit as maybe tan H or sigmoid. Okay, so this is typical first layer, fully connected layer, and then we stack another layer that transforms these values into just a single scalar value. Okay, single scalar value. And then this guy is fixed, but this guy is replaced by each of these four different vectors, and thus we have a 4 different scalar value, right? And that scalar value will be further given to the softmax layer so that we can generate this probability distribution. So that is the third realization of our attention model. Okay, any questions so far? Okay, then let's take a break and then continue at 3:25. 아, 네. 이게 CS24N의 그 중간고사 그것들이 좀 있더라고요. 아, 그게 있어요. 네. 그래서 그것들 좀 공부하면 될 것 같아요. 네. 아주 얼마나 내가 창의적으로 낼 수 있을지 모르겠는데 거기에서 좀 한번 적극적으로 좀 내보려고 합니다.
마지막 세 번째 스코링 방법이요. 그게 싱글 레이어여서 XOR 문제가 해결이 안 되는 단점이 있다고 했잖아요.
아, 동영상에서요?
네.
세 번째?
네, 이거.
이거요?
네,
아, 네.
얘가 뉴럴넷 접근으로.
아, 네.
근데 그게 싱글.
네.
그게 문제가 그거에는 논 리니어한 바운더리를 못 만들고 리니어한 바운더리를 만들어서 한 거잖아요. 그러면
네.
2번도 마찬가지인 거 아니에요?
아, 2번도 아, 2번도 못 만드는 거 아니냐?
네, 똑같은 거 아니에요?
그럴 것 같아요. 네.
근데 그냥 싱글 레이어가 XOR 문제를 해결을 못한다라는 것 자체는 이해가 되는데
네.
그게 이 스코어 펑션에서 왜 그게 단점이 되는지 잘 모르겠어요.
아, 그 XOR랑은 좀 상관은 없을 것 같고요, 이거는.
네.
그러니까 이거를 어텐션 웨이트를 구하는 어떤 식인데
네.
그거를 아무 파라미터도 없는 이런 식.
네.
그리고 파라미터는 있지만 뭔가 여전히 두 개 이제 곱의 리니어한 형태로의 이런 식. 그래서 여기가 이제 파라미터 옵티마이즈가 되는 거죠.
네.
그다음에 이거는 이거랑은 좀 형태가 다르긴 하지만 어쨌건 레이어를 하나 쌓았고 여기서 한 H를 통과한 다음에 어쨌건 선형 레이어를 하나 더 쌓은 것이기 때문에 여기서 그러니까 이거는 2레이어 뉴럴넷인 거죠. 얘네들이 1레이어 뉴럴넷이냐? 그런 건 아니지만 어쨌건 얘는 지금 투 레이어 뉴럴넷인 거잖아요.
2레이어인 거예요.
네, 그러니까 이게 요거 두 개 다 인풋으로 들어왔고 여기서 이제
근데 어차피 탄젠트는 그 뭐지? 피스와이즈 펑션이어가지고
피스와이즈?
그러니까
네.
네, 그러니까 여기서 WAHT
네.
이거 계산한 거에
네.
매트릭스로 들어가는 게 아니라 어차피 하니까 그냥 이 부분이 원 레이어 아니에요?
여기까지가 이제 리니어 트랜스포메이션
네,
하는
네,
거고요. 여기는 거기서 나온 벡터들. 그러니까 여기서 예를 들면 5개로 뺐다. 그러면 이 5개 각각에다 탄 H를 걸어주는
네,
거니까.
네.
그러니까 여기까지가 이제 탄 H고요.
네.
그 다음에 여기다가 이제 내가 이거 하나를 뽑는다 그랬잖아요.
네.
그 하나를 뽑는 과정이 이제 웨이트를 생각해 보면 이 5개 개수에 해당하는 웨이트가 있겠죠. 그러니까 5디멘전al 웨이트가 있겠죠. 그래서 얘네들한테 웨이트가 걸릴 건데, 그 이제 두 번째 레이어에서 웨이트가 이제 요 놈이에요. VA.
그러면은 얘도 학습으로
네.
다 결정이
네.
되는
네.
거인 건가요?
맞아요. 얘도 학습으로, 얘도 학습으로, 얘도 또 학습으로. 네.
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 그러니까 이게 일단은 레이어가 2개짜리 뉴럴넷이니까 그런 뭔가 난리니어러티를 좀 저게 구현할 수가 있다는 얘기죠.
근데 그냥 얘는 어떻게 보면은 점수화를 해서
네.
어텐션을 뽑는 거잖아요.
네.
근데 그거랑 논리니어티랑 무슨 상관이에요?
아, 그러니까 점수가 뭔가 내적을 하면 기본적으로 내적 값이 높으면 점수를 높게 부여를 받을 거잖아요.
네.
근데 어떤 경우에는 내적 값이 높아도 점수를 좀 작게 줘야 될 때가 있다는 거죠.
네. 어떤 경우?
네? 어떤 경우냐고요?
네.
아, 그러니까 이제 뭐 그다지 모르지만 내부적으로 뭐 네. 우리는 하여튼 난리니어한 어떤 그 스코어 값을 가질 수 있도록, 그러니까 내적 값에 그냥 단순하게 내적 값에만 비례해서 스코어가 나오는 게 아니라 내적 값이 크더라도 뭔가 스코어 값이 작을 때도 있고 클 때도 있는 이런 거를 좀 여기서 좀 플렉서블하게 좀 구현을 하려고 이렇게 투 레이어로 구성을 한 거죠.
또 다른 건데 왜 LST 그러니까 게이트에서 LSTM이나 뭐 GRU에서 게이트에서 시그모드 쓴 건 이해가 됐는데 왜 탄젠트 하이퍼볼릭 탄젠트를 쓴 거예요?
그게 이거를 내가 좀 설명을 아마 수업 때 좀 쉬는 시간 끝나고 좀 해주면 좋을 것 같고요.
네.
이게 일단은
그러면 수업 시간에
그렇게 해요. 네.
하고 하는
네네.
로컬 로테이션에서
네.
그러면은 어떻게 하면은 그 히든 스테이트 뽑는 기준이 어떻게 되는 거예요? 글로벌은 다 되는 거니까 이해가 되겠는데
그 로컬 어텐션은 몇 개만 그 내에서만 하는 거죠?
네.
아, 그거는
그
나도
서브셋을 어떻게
네, 그거는 나도 잘 모르겠어요. 그거를 실제로 로컬 어텐션을 쓰는 경우는 나도 거의 못 봤거든요.
거의 글로벌을 써요. 근데 글로벌을 쓰면은 학습 속도가 그러니까 시퀀스가 매우 긴 경우에는
네.
그러면은 그 글로벌 그 윈도우 개수를 하이퍼 파라미터로 정해놓고 하나요? 다 하기엔 너무 길잖아요.
아, 네. 그러니까 그 인풋 시퀀스의 길이가 결국 우리의 어텐션의
길이가 크기?
네, 그렇죠. 어텐션 벡터의 길이가 되는 건데 그거를 그러니까 제한을 시키죠. 아까 그 트렁케이티드 그거 있잖아요. 그래서 그게 시퀀스가 몇 이상이 되면 그냥 뚝 잘라 버려요. 네.
그 자르는 기준은 딱히 없나요?
아, 네. 그거는 우리가 좀 사전에 그냥 정리를 해요. 네. 네.
이걸로 텍스트 많이 아무리 봐도 이게 그 잊어버리면 제가 저건 가만히 있어요. 알프레오 둘 놓치 모니터 마우스 주머니 가운데 있는 주머니보다 새로워. 너무 버려.
귀엽게 생기지 않았어. 많이 차이났어.
Okay, so let's continue. So yeah, let me clarify one more thing here. So in this last item, this guy, HT and HS and WA, this WA is represented in this, yeah, in this linear or fully connected layer's weight, right? And then suppose that is having the dimension of 5, and then I mentioned that this one will produce a single scalar value, and then this part, okay, that part of this guy is represented by this VA transpose, right? So VA is corresponding to this part, VA, right? So that way, it's basically two-layer neural net where the output is the single scalar value that doesn't have any nonlinear unit at the end. It's just a linear layer output, right? Of course, these values will be fed into the softmax layer, right? Okay. And then, one student also asked about why we are using 10H as the main nonlinear unit in the RNN or LSTM or GRU. So yeah, in LSTM or GRU, I mean the output that works as a gate, like a forget or input and output gate, will all be generated by this sigmoid layer, right? So that ranges from 0 to 1, which will be multiplied element-wise with certain signal vectors. But yeah, in the original RNN, also in this LSTMs or also GRUs, this 10H is working as the nonlinear unit that generates the meaningful signal instead of just a gate. And then why are we using the 10H as main nonlinear unit in RNN or LSTM? Okay, so that is related to the main property of a recurrent neural network that actually uses the shared parameters. So in the previous example, where we had a like H1, 2, 3, and so on, and then suppose this H1 was suppose the main point of using 10H is because it is zero-centered. Okay, so zero-centered means the ranges are between -1 and 1, but in the case of sigmoid, the range will be 0 to 1, right? And then as I showed previously, so it's like multiplying with an A and then this X and then multiplied by B and C will be added together, right? And then that will form our H2. And then this one will eventually I mean, I'm talking about the original RNN, and then this original RNN, this H2 will also go through this 10H nonlinear unit. But suppose we are using sigmoid, where the ranges are between 0 and 1, and then also this one after going through the sigmoid, and then it will have the range of 0 and 1, right? Okay, and so this ranges of our signal is actually like a biased towards the positive values. And then, yeah, so yeah, we are doing the same thing of like multiplying. Yeah, we are basically doing this thing, AHT minus 1 and BXT plus C, right? And then this guy this guy is ranging from 0 to 1, right? And then so yeah, given this value, when HT minus 1 was a sigmoid output ranging from 0 to 1, and then we will, after doing this linear transformation, and then that will also go through the sigmoid unit, right? And then this one, this one will also be in the range of 0 to 1, right? I mean, that is not the point. I mean, the point is to carefully handle the ranges of range of that input value of our sigmoid. Okay, so in the case of sigmoid, as you guys know, the most sensitive regions or this desirable range of our input signals are around 0, right? And then this HT minus 1 is already biased towards the positive. And then suppose this, of course we have a C. So if C was maybe negative 0.5, and then it can be shifted back towards the around the 0. And we can also move the majority of these signals into the range of 0. But this guy will be also mapped into some sigmoid value, and then this is HT, and HT will be further multiplied with this guy and this, right? And then here, suppose this guy also had a 0 to 1, but this range, the actual range was like, suppose this actual range was like 0.2 and 0.5. So this is the range. I mean, suppose that was the actual range for H1, for example. And then this guy was had a range of 0.3 to 0.6 or 0.7, for example. And then this actual ranges may shift a little bit to the left or right, right? So in that case, we may need a different bias values at different time steps. But in this case, because simply we are using a recurrent neural net that shares all these parameters, so we cannot have a different biases as we need across different time steps. We have to use a common, I mean, same value of this bias value, right? So in that case, it cannot properly handle, or it may be really sensitive to how to set up this bias value, and then it may easily be falling into the range of this guy in terms of our sigmoid value, which is kind of a insensitive range, right? So because of this kind of region, this signal for this HT or HT minus 1, if that is already zero-centered, and then it might be more, I mean, much easier to set up this bias, because this bias at least doesn't need to carefully calibrate this biased signal of this HT minus 1, right? Okay, so that is at least my kind of justification or interpretation of why we are using 10H, which is already zero-centered in this recurrent neural network. And also it is the same thing in the LSTMs as well. Okay, then one interesting see. Okay, so here, yeah, when using our decoder, suppose this guy was our generated token in the second time step, and then we are actually feeding it into the next time steps input, right, in our RNN cell. And then yeah, actually this information may not be necessary, because this information of keyword poor was generated from the softmax layer, I mean the linear layer, and then the softmax layer by using this vector H2, right? So that worked as the input that creates this Y2, and then this RNN cell is taking the input as R2, right? So in this case, this giving additional input of Y2 is not necessary, in some sense, right? So in this case, we may just discard this. But in our lecture, so the lecture is discussing the needs of, why we have to provide this explicit output that was generated here in addition to H2. So what was the reason for it? If you guys watched the lecture video carefully, and then you guys should know, I think. 이거 아는 사람? So why are we giving the input of the generated output in addition to H2? Because H2 conveys the information that will generate this Y2. 이거 아는 사람 없어요? 강의 나오는데. 한 명도 없어요? 이미 나온 걸 모델한테 알려주기 위해서. 뭔가 봤네요. 그럼 왜 저게 없으면 중복된 게 나오죠?
히든 스테이트에서 가지고 있긴 하지만 직접적인 Y2에 대한 아웃풋이 들어가는 게 아니니까 확실하게 나왔다라는 걸 알려주는 게 조금 더 확실해지기 위해서는 전에 답을 인풋을 넣는 게 더 확실하게 모델이 나왔었으니까 나왔지 않다고 알려주는 거.
네. 거의 이제 맞는 어떤 해석인 것 같고요. So yeah, let me add also my own interpretation in addition to the student's answer. So if H2 was 1, 2, 3, and then it generated maybe the softmax output as 0.1, 0.2, 0.1, 0.3, maybe 0.4 and 0.2. So suppose our vocabulary was having the length of 5 or 5 different unique words. Okay, so in this case, this RNN, I mean, it's kind of my part of my own theory, but this RNN already knows the transformation from this vector into this softmax vector, because it's basically a linear transformation that this RNN cell already contains, and then doing the softmax layer, right? And then I think in terms of the amount of information, RNN will definitely know this guy will be generated from this vector, right? So I think by just giving this information to the next step's RNN cell, and then it will already know this softmax vector in the previous time step will be like that vector, right? But in this case, we can, so it is a kind of a different story in terms of what kind of output that we actually generated from the softmax vector. So will we use the argmax stuff, or we will use the greedy, beam search thing, and maybe this kind of ancestral sampling or something like that. Yeah, there was a method called the ancestral kind of sampling or something, right? So what does that do in order to generate the output from this softmax vector? Ancestral sampling. How does it work? It is actually sampling some keyword from this this softmax vector, not just selecting the argmax one. So here in this case, the argmax one is this guy, right? But if we do this stochastically, and then we can actually perform actual sampling from this distribution. So in that case, we can choose this word with the probability of 40, and then we can choose this word with the probability of 20. So in that case, our output vector is actually not the same as that softmax vector. We need additional process that can be dependent on our particular strategy, so that we can generate the actual output token in this particular time step. So in that case, there are several different strategies and scenarios, right? And then in the case of an output that generated, maybe, let's say we perform this argmax thing, which is just a greedy, simplest greedy version of our decoding step. And then this one was maybe study, okay? No, it's a poor, for example. And then in this case, in terms of this vector representation, we can represent that vector, that output vector, of course, as 0, 0, 0, and 1, 0, right? And then this one is equivalent information that means we generated the poor, which corresponds to fourth dimensional entry as our actual target, actual output word in the second time step, right? So as you can see, there is certainly the discrepancy between this vector and this vector, right? Those two are quite different vector, right? Yeah, so in this case, even though neural net knows that the softmax vector will be like that, given this hidden state vector of an H2, but yeah, this neural net doesn't know the actual keyword that was generated in this time step, right? And then, yeah, we are explicitly giving this information as well into this next time steps RNN cell. Okay, and then in practice, yeah, as the student mentioned, in practice that actually works. That plays a role of preventing from generating additional, the redundant keywords, right? Redundant keywords, because that in this RNN cell, that can actually, yeah, that is actually capable of generating a different keyword that is kind of different from that input keyword that were given in this time step, right? So yeah, that way they can kind of avoid the situation like generating the same tokens over and over. But yeah, yeah, I don't know. I don't understand exactly how it can avoid this kind of repetitive or redundant kind of keyword generation. But yeah, but anyways, giving this information is quite different, or additional information to that softmax vector. Okay. And then the last thing that I wanted to mention was the bipair encoding. So it's mainly used for the subword encoding or registering these subword level or character level n-gram kind of thing into our dictionary. Okay, so yeah, when searching for this bipair encoding, which is quite widely used technique in the NLP. So yeah, it came up with this Wikipedia articles as the first one. So it's like this. So given this particular character level kind of sequence, and then we find out the most frequently appearing character 2-gram. Okay, so just a sequence. Yeah, we look at the sequence of the two characters. And then suppose that frequent, the most frequent character level 2 bigram was AA, and then we register this bigram into our dictionary, and then we assign a new index in our dictionary, and also that is represented as this Z, and then we replace this Z into the sequence of this bigram of AA. And then from the sequence, we also look at the most frequently appearing bigram. So here Z is also another character that we newly register into our alphabet, ranging from A to Z, which is just a unigram of characters. Character level unigram, and then we added the most frequently appearing character level bigram. And then we replace or re-represent our sequence by using augmented dictionary, and then from there we find out the most frequently appearing bigram as well. And then this Y is also found, and here. Okay, so in this case, the most frequently appearing one was, here in this case, zy was appearing twice, right? So here z and y are considered as another kind of character. So this is done, okay? I mean, this is done until we no longer find any more frequently appearing bigram of our characters. And actually, it can be done until we find no bigram that appears more than once. Okay, so in this case, every bigram is just appearing once, right? So this is the extreme end that we can stop our algorithm. But in practice, in our NLP stuff, if we do this kind of thing, and then our dictionary will explode, and we are also restricted to some memory size in terms of the size of our dictionary that we can maintain, and thus in that case, so in that case we start with a predefined maximum length or size of our vocabulary, right? And thus we increase or expand our dictionary until that maximum entries are registered. Okay. Okay, and then I found there are a few papers on this bipair encoding in the NLP domain, and then this again, as I mentioned, this is quite frequently used techniques in many of the NLP domains, and also it has the advantages of handling this rare words or out of vocabulary, because the entire one particular word may not have appeared in our training data, and thus it was not registered in our dictionary, in a word level dictionary. But if we use the character level one, and then this newly appearing keyword is represented as the sequence of some known character level sequences, right? Or subword or character n-gram level sequences. And then here, in this case, we typically don't across the border of different keywords. Okay, so here, let's see. So in this case, I go to school. So in this case, it's basically starting with the character level dictionary, and then we have a space here, but space, is represented as this dot. So that is registered as a special character in our dictionary. Okay, and then in this case, our bipair encoding is looking for the character level bigram up to this point, I and space. But if you found this space, and then we do not reach out to this, so suppose this guy, is encoded as large Z, which is registered newly to our dictionary, and then this Z and G is not considered as our candidate to be added to our dictionary. So we don't cross across different keywords when doing this bipair encoding. Okay, so I think that's all that I prepared for in terms of this that I wanted to discuss in the class. So the next class we will have an exam. And then yeah, I haven't decided what to add, or what kind of problems we will be looking at in our exam. But yeah, I'm planning or thinking of highly utilizing those exam questions available in the CS224N as a midterm, like practice or previous year's exam, and also this year's exam as well. Okay, and 마지막으로 좀 이야기를 하면 별로 좀 열의가 안 보여요. 이거 대부분의 경우 다 그런 건 아니겠지만, 뭐 이 강의가 뭐 안 좋아서 그럴 수 있을지, 아니면 뭐 내 강의가 부족해서일지, 뭐 여러 가지 원인이 있을지 모르겠는데, 일단 내가 가르치고자 하는 열의에 거기에 못 미치고 있는 것 같아요. 내가 가지는 느낌은. 일단은 뭐 한 5분 이내로 좀 잔소리를 하면, 뭐 일단은 뭐든지 좀 공부할 때 좀 전투적으로 좀 달려들어야 돼요. 이게 뭐 자기가 이거 뭐 이 강의 렉처 비디오 뭐 50분짜리 아니면 1시간 20분짜리 봤다 그러면, 뭐 하여튼 내 학생들은 뭐 여러 번 들어서 뭐 지겨울 수 있겠는데, 자기가 뭘 알고 있는지는 확실히 알고 있어야 돼요. 뭐 일단은 질문이 없고, 내가 강의에서 나온 거를 질문을 했을 때 모르고 있고, 그건 진짜 부끄러운 일이에요. 그러니까 뭐 똑같은 걸 봤을 때 뭐 누구는 뭐 거기서 뭐 70%를 깨닫고, 혹은 흡수를 하고, 누구는 이제 90%를 깨닫고, 그래서 쟤보다 내가 20%를 더 모를 수는 있지만, 그 20%에 해당하는 내가 모르는 부분이 뭔지는 알아야만 그걸 나중에 내가 해결을 할 거 아니에요. 이 강의가 뭐 재미없다라고 생각해, 아니면 뭐 별로 뭐 잘 못 가르친다, 뭐 어떤 학생은 뭐 일부는 뭐 옛날에 뭐 이 강의는 뭐 나랑 안 맞는다라거나 뭐 이렇게 얘기도 하고, 뭐 그런 것도 뭐, 그러니까 이 강의뿐만 아니라 뭐 좀 뭐 재미없거나, 뭐 사실 좀 뭐 잘 못 가르치거나, 뭐 하여튼 뭐 잘 떠먹여주고 재밌게 해주고, 다 오르고 달르고 해갖고 떠먹여줘야 뭐 사실 자기도 먹고 싶지, 뭔가 이렇게 좀 척박한 상황, 뭐 이런 경우 뭐 좀 하기 싫을 수 있고, 뭐 그럴 수 있는데, 그래도 뭐 하기로 한 이상 좀 확실하게도 좀 하고도 넘어갔으면 좋겠고요. 이거 했는데 모른 채로 지나가면 뭘 공부해도 다 똑같아요. 뭐 별로 진전이 없고 발전이 없어요. 왜냐면 아까 뭐 똑같아요. 뭐 이걸 봐도 내가 뭘 모르고 있는지, 뭐 대충 뭐 한번 봤으니까 뭐 한 여기서 이야기하는 뭐 20, 30%, 30, 40%, 40, 50%, 50, 60% 정도 뭐 내가 흡수했겠거니. 그게 중요한 게 아니에요. 하여튼 하여튼 뭔가 이걸 했을 때는 자기가 좀 하여튼 일단 내가 이렇게 이걸 뭐 가르치는 사람이기 때문에, 뭐 내가 이거를 더 책임감 있게 더 공부를 많이 해와서일 수도 있기도 하겠지만, 그리고 뭐 사실 원 오브 댐으로 여기 앉아있는 뭐 4, 50명? 뭐 이 정도 학생들, 자기가 뭐 50명 중에 한 명이면 뭐 그냥 뭐 노바디로 그냥 여기서 뭐 있다가 이렇게 뭐 나갈 수도 있겠지만, 뭐 일단은 나도 이거를 사실 나도 공부하려고 이거를 뭔가 선택을 해갖고 이 강의를 진행을 하기로 뭔가 한 거고, 나도 아는 게 있고 모르는 게 있고, 뭐 내가 아는 게 여기까지 있었고, 여러분들이 아는 거는 뭐 한 이쯤까지 있겠죠. 물론 나보다 어떤 부분은 더 아는 것들이 있겠죠. 그러니까 XOR을 따지면 내가 뭔가 어떤 여러분들이 내 부분 집합이고 내가 여러분들이 이제 슈퍼셋은 아니고 분명히 이제 벤 다이어그램에서 여러분들 많이 아는 거 내가 또 모르는 게 분명히 있을 거고 내가 또 아는 것들이 또 나만 아는 것들이 또 있을 거고 뭐 그럴 텐데 일단 중요한 게 하여튼 뭐 기본적으로 내가 여러분보다는 좀 많이 알겠죠. 뭐 그러면 사실 좀 눈앞에 보이는 저 타겟 뭐 네, 그러니까 하여튼 저 사람만큼은 내가 알아야지. 그러니까 나는 이 갭을 줄여갖고 이렇게 해갖고 이 사람을 내가 이렇게는 네, 이 과목을 들으면서 여기까지는 내가 가야지. 저 사람 아는 것만큼은 내가 싹 다 흡수를 해야지. 막 이런 식으로 해야 여러분들이 발전을 하고 성장을 하고 경쟁에서 살아남고 경쟁력을 가지게 되고 그래요. 네. 근데 하여튼 그런 네. 실제로 그런 태도를 보이는 학생들이 굉장히 성공하고 또 그런 태도를 보이지 못하는 학생들이 또 굉장히 실패를 하고요. 실제로 나도 짧은 교수 생활이나 막 그런 케이스들을 극명한 케이스들을 봐왔고, 네. 하여튼 뭐 그래서 열심히 좀 한번 하세요. 네. 네. 뭐 이게 뭐 이 과목을 뭐 이렇게 탑 프라이어티로 여러분들이 다른 하고 있는 것들도 많은데 뭐 내가 강요를 할 수는 없겠지만 네 그냥 뭐 전체적으로 좀 모럴 아니면 좀 사기 아니면 의욕 이런 것들이 좀 강의를 이걸 제대로 봐오긴 했나 뭐 싶을 정도로 뭐 다 봤을 수는 있겠는데 뭐 또 잔소리 같은 얘기를 하면 나는 뭐 이런 거 강의 보면 거의 토시 하나 안 놓치고 좀 들으려고 해요. 물론 이 소초가 막 100% 막 얘기하고 올 때는 그냥 손 놓긴 했는데 어느 정도 그래도 좀 내가 생각할 수 있는 범위 내에서 좀 그래도 좀 붙잡고 쫓아갈 수 있겠다 싶은 것들은 아까 얘기했던 것처럼 뭐 모르는 얘가 한마디 뭐 아무것도 아닌 것처럼 쑥 지나가면서 그런 게 되게 중요한 거예요. 그런 게 진짜 그 사람의 깊은 인사이트에서 나온 한마디고 그거를 내가 이해할 수 있고 내가 흡수할 수 있어야 내가 그 사람과 갭을 좁힐 수가 있는 거거든요. 그래서 나 같은 경우 나도 이제 이 사람들과 갭을 좁히기 위해서 그렇게 좀 강의에서 좀 한 문장 한 문장 좀 놓치는 거 없이 최대한 좀 하려고 하고 그러니까 아까 예를 들면 뭐 그런 얘기도 이게 뭔 얘기인가 그런 것도 이제 그냥 뭐 그런 거를 누군가 여기서는 몇 명은 한 10%? 20%? 뭐 샤이해갖고 이야기를 안 해주는 거였으면 뭐 다행이겠지만 뭔가 뭔 소린가 그런 얘기가 강의 어디 나왔다는 건가 이런 표정을 하고 있는 학생들이 뭐 많았거나 아니면 뭐 하여튼 뭐 그래서 뭐 여기까지 하고요. 일단은 시험을 다음 주에 그렇게 좀 진행을 하기로 하고 잘들 하여튼 준비하고요. 그러면 나는 아마 다음 주에 출장이라 이제 시험은 여기 다른 학생들이나 이제 조교 통해서 진행을 하겠지만 하여튼 뭐 잘들 보고 다음 주에 또 보기로 하죠. 뭘 볼지는 또 내가 공지를 또 해주도록 할게요. 그래요. 수고했어요.